Now, to solve an initial value problem for a second order ordinary differential equation using the Laplace transform, we apply the Laplace transform to the left hand side and to the right hand side. Then since the Laplace transform converts differentiation to multiplication, the differential equation is going to be converted to an algebraic equation. And then by solving this algebraic equation for the Laplace transform of the unknown function, we can find the Laplace transform of the unknown function. And then using these two facts, the fact that the Laplace transform is 1-to-1 and that the inverse Laplace transform can be computed, we are going to compute the unknown function itself. Well, but these two facts, they are not easy, so I'm not going to be able to prove them because the proof is very complicated and it uses complex analysis. Then if I just want to solve differential equations using Laplace transforms just like that, then it's far too complicated. It's much more complicated than doing it directly, right? So what we usually do, we have a table of pre-computed Laplace transforms, and then when we compute the Laplace transforms of the right-hand side of the differential equation, and when we compute the inverse Laplace transform of the result, we do it using the table of Laplace transforms, other than the explicit formula for the inverse Laplace transform. So, but then I'm going to go through an example, but still I think it's a bit complicated. So the real usefulness of this Laplace transform is not to solve differential equations that appear in our class, but rather differential equations that appear in electrical engineering, where the right-hand side may be discontinuous. So then the Laplace transform becomes really useful. But since I'm not teaching electrical engineers, I'm teaching mathematicians, and we do not really need that. And then if you are interested, you can always just read the next section of the textbook. It's not, it's not rocket science, but it's just I don't think that that an effort that we would spend on developing Laplace transform until to the point where it is really useful for electrical engineering is worth spending our time in. So what I'm going to do is just for your education, I'm going to go through a more complicated problem on solving the initial value problem using the Laplace transform, so you can understand how it works. And then if you ever need it in future, it's very similar, only probably, well, some things may be a little bit more complicated. But so what do we have here? So the Laplace transform of y double prime is s square times the Laplace transform of y. So I'm going to denote the Laplace transform of the unknown function is going to be y capital, right? So then the Laplace transform of the second derivative is going to be s square y minus s times y of 0, and y of 0 is 1, so minus s, and then minus y prime of 0, which is 0, so that's just it. So then the Laplace transform of the first derivative is s times the Laplace transform of the unknown function minus y of 0, so minus 1. Right? So substituting it to the ODE, I'm going to get s square y minus s plus 2 times sy minus 1 plus 5 y capital equals cosine of 2t. So how do we find the Laplace transform of cosine of 2t? This is usually just pre-calculated. So let me show you a table of Laplace transforms from Wikipedia. Right, so cosine of 2t is here. So this is cosine of 2t. That's the Laplace transform of cosine of 2t. So s over s squared plus omega, and omega is 2. So it's going to be s times s squared plus 4. Okay, so now putting all the terms with y together, we get s squared plus 2s plus 5y equals s over s squared plus 4. Then I have minus s on the left, so plus s, and I have minus 2 on the left, so plus 2. Right? So which means that my y, which is the Laplace transform of the unknown function, is going to be 1 over s squared plus 2s plus 5 times s over s squared plus 4 plus s plus 2. Now, the next step is to express it as a sum of partial fractions, right? So the sum of partial fractions here is, and now if you really wanted to solve it just by hands, it would probably take half an hour just to simplify everything and to get the partial fractions. So of course, which is why I'm saying that the method of Laplace transform is probably, even if you use the table of Laplace transforms, is more complicated than just solving it directly. So, but I'll just give you the answer, s plus 8, which you can get by just entering this expression into Wolfram alpha. It'll give you partial fractions immediately. So over 17 times s squared plus 4 plus 8 over 17 times 2s plus 3 over s squared plus 2s plus 5. Okay, so these are the partial fractions. Now, the next step is to apply the inverse Laplace transform to this. So let me do it. So let me rewrite it. So the Laplace transform of the answer is s plus 8 over 17 times s squared plus 4 plus 18 over 17 times 2s plus 3 over s squared plus 2s plus 5. Now, let us look at this term first. So in order to figure out what y of t is, we need to look for a similar pattern in the table of Laplace transforms. Well, and then by looking at it, you notice that we have it is similar to the Laplace transform of the cosine, and it is also similar to the Laplace transform of the sine. Well, for the Laplace transform of the cosine, we must have s in the denominator, so in the numerator, and for the sine, we must have omega, where the denominator has omega squared. So let me rewrite this in the right fashion. So this is 1 over 17 times s over s squared plus 4 plus, we have 8, right? So I'm going to write 1 over 17 times, in order to have something like this sign, the denominator is s squared plus 4. 4 is 2 squared, so for the sine function I should have 2 here. Well, but then the total product is 8, so I need to write 4 so that it is correct. Right, so then this term gives us 1 over 17 cosine 2t, and this term gives us 4 over 17 times sine 2t. Okay, so the first term gives us well, a combination of sine and cosine. Now how about this term? So what are we going to do with this? So here we have a linear function in the numerator and a quadratic function in the denominator. So let us look at the table of Laplace transform. So where do we see a pattern like this? Yeah, and then you start analyzing it, and then you see that what we have is actually exponentially decaying sine wave and exponentially decaying cosine wave. So this is our reference now. Well, but then in order for this to match our example, the denominator must be presented as the sum of squares, right? So we need to complete the square. So let me rewrite it. So here I'm going to have 8 over 17 times the denominator is s plus 1 squared plus 4, and 4 is 2 squared. Right? Okay. But then the numerator should be a combination of s plus alpha and a constant. So alpha here is 1. So what I must have is a combination of s plus 1 and the constant. Okay, so I'm going to write s plus 1 first. So s plus 1, in order for this whole thing to be consistent, I must multiply by 2. Right? So then I'm going to have 2s plus 2, and the original expression has 2s plus 3. So I'm going to write plus 1. But then furthermore, if you look at this expression, then the numerator is omega, where omega squared appears in the denominator. So in other words, in my case, omega is 2, so what I should have is not 1, but 2. But of course, if it is 2, then I should write 1/2. Okay, so now my right-hand side, well, my second term can be rewritten as 8 times 2 is 16 over 17 times s plus 1 over s plus 1 squared plus 2 squared plus 4 over 17 times 2 over s plus 1 squared plus 2 squared. And this is 16 over 17. Then s plus 1 gives us e to the minus t. Then this term is, I think it's cosine. Yeah, so we have s plus alpha, so this is cosine. This is cosine of 2t plus 4 over 17. And this is still e to the minus t sine 2t. So the final answer is that y equals 1 over 17 cosine 2t plus 4 over 17 sine 2t plus 16 over 17 e to the minus t cosine 2t and plus 4 over 17 e to the minus t sine 2t. Well, so in a way we got the answer at once. So we just apply the Laplace transform to the right hand side, but notice that I skipped a lot of fine details. So for example, I did not explicitly do partial fractions. I did not pre-compute all these Laplace transforms. So it is still, even given all that work that we kind of skipped on, it still took considerable effort to do this. But anyway, so that's how the method works. So again, so in order to solve an initial value problem using the Laplace transform, what we do, we apply the Laplace transform to the both left-hand side and the right-hand side of the differential equation. Then this gives us an algebraic equation on the Laplace transform of the answer. And then we apply the inverse Laplace transform after a lot of algebraic calculation. We apply the inverse Laplace transform, and this gives us the final answer. So the